Hello, welcome to our EEE 473 term project, which is called as FemBeam Computed Tomography. My name is Öykü Karavelioğlu and my teammate is Ecem Şimşek. We are mentioning our process results and interpretations in the following order. Here is the table of contents. As you can see from the figure 1, the FemBeam geometry is nothing but a rotating sensor and detector which can be aligned to an arc or a line. We choose arc geometry. We calculate the theta L in polar coordinates as such equations. Two different techniques are used in this project. FemBeam built-in function done by MATLAB and hand-made projection function by using built-in radon. In built-in function, the image is projected like parallel beam, then converted to FemBeam. In our function, after taking the radon transform, the theta and L values are calculated and then stored in a matrix. First of all, to see the base case without any non-ideality, we project three datasets and their sinograms. Since we use two different methods, we got chance to compare the result. The distance, the difference in sinogram can be detectable. The reason of it is built-in stores the radon values in different indexes compared to ours. But as long as the values are correct, it can be handled via flipped angles. In back projection, we also use two methods. One of it is again built-in, but the other one is this time we used external codes by arranging its parameters and in a references part in the report. Similar to FemBeam projection, built-in iFemBeam converts the sinogram into parallel beam structure. Then filters are applied and lastly the function takes its inverse radon transform. The filters are sheep log and ram log, which are multiplied with projections in frequency domain. Aliasing is avoided by zero padding. In the alternative approach, filtered back projection is applied, and the parameters can be listed as starting angular values, the size of output image, the distance between source and the detector and the object, etc. It can be seen in the a back projection of the original image, which is quite similar to the original one. Also in real life, some of the non-idealities can distort the image. Noise is one of it, and the typical noises in CT are Gaussian, Poisson, impulse, and quantization. Most common ones are Gaussian noise and the impulse noise. Gaussian noise is more homogeneous, affects every pixels, but impulse noise is inhomogeneous and affects pixels individually. Namely, it doesn't distort the image as a whole. To simulate the Gaussian noise, AWGN is created and added to the both in sinogram data and original image. The reason is that since the human body size can affect the imaging, the noise is added in original image, and CT machine can create noise, both create noise, so that sinogram values are noised by this function. Both are considered. First, different noise levels are added to sinogram. The values can be seen in the figures, and then they are back projected. Second, the noise is and here is the back projections. Second, the noise is added to original image, and the sinogram is also noisy, and which means the output is also affected. As a conclusion, in high levels of noise, phantom brain is affected more compared to other datasets. Its contrast decreased significantly also. Distance also another factor that we change. Since it is a measurement between source to origin, it causes 2 times change in distance from the geometry, distance from between source and the detectors. On the left figure, D is determined as 750 millimeter, and on the right, since sinogram D is 1000 millimeter, the results show that MATLAB built-in function can optimize the sensor data, but function done by hand needs further adjustments, such as decreasing detectors and rearrangement of it. Also, the value can blur the image as well. Fan size is another parameter that affects the quality of the image. The results are obtained by fixing the values to 360 millimeters, which are optimized by the MATLAB built-in function, and use this value. And fan angle is changed in the range 20 to 40 degrees. then obviously field of view is changed and the results are either zoom in the tissue or lost its contrast so that no details could be distinguished. Thanks for listening to me. Afterwards, Ecem will continue.
Now I can continue from different filter types. So as we can see on the slide, we first of all wanted to try out different filter types in order to show it and represent it in our project as a non-ideality or a real-life condition. So here in the slide, we can see first of all how important filtering is, because here on the left-hand side we have a filtered image, and on the right-hand side we have a non-filtered image. So as the name of the filtered back projection suggests, if we apply only back projection, then we will be obtaining very bright and blurred images. And the reason behind that is when we are applying the back projection algorithm, we are basically smearing out all the projections through the entire image. So if there is a projection that is very bright, then its brightness and blurredness will be spread out onto the whole image, so that the unfiltered image will be very bright and blurred. And in order to prevent this, we use different type of filters, especially sharpening and high pass filters, in order to cancel the effect of these blurs and brightnesses in the image. And we also give importance to the fact that while we are using high pass filters, we try to choose them as softened filters in order to not to increase the effects of a possible noise in the image. So first of all, on the slide, we can see on the left-hand side, we applied the REM-lag filter to our image coming from the first dataset and no filtering on the right-hand side. So also, we applied filtering to our second image as well. This shows a brain, for example. Here we applied to it a cosine filter. And on the right-hand side, we can see the non-filtered version of it. And here also we have the chest image, and we can see the hand filter applied to it and no filter applied to it on the right, as we can see here. And when we tried out different filter types, we observed that different types of filters did not much differences from each other, but filtering was very important as an overall procedure, so that we saw how filtered back projection relies heavily on filter types, because here, as we can see, the left-hand side and right-hand side images have drastic changes, as we can see here. Here on this slide, we can see the animation of filtered back projection. So up until this point in our project, we worked with the ifnbean built-in function of MATLAB in order to perform our back projection algorithms. But as we can see here, filtered back projection occurs in such a manner by going through the whole sinogram and constructing it into a reconstructing image. So, for example, in order to observe this procedure in MATLAB, we found some external MATLAB codes on GitHub that we wanted to implement this procedure on MATLAB. And this external code also gave us the chance of tuning a lot of parameters while we are performing the back projection algorithm. So first of all, we applied these external codes to our first image coming from our first dataset. And here we can see the reconstructed image that we obtained at the end. So although it is not very successful as compared to the built-in functions of MATLAB, we can see that it still caught the main features that are present in the image. So it can be considered as a successful attempt. Plus, for example, we observed a lot of tunable parameters, as we can see here. For example, source to object distance, source to detector distance, fan beam angle, starting angular position, total angle, and a lot of other parameters. And we were able to see their effects, for example. So overall, as an exemplary case, decreasing the source to detector distance, for example, made the image better as a starting case. Increasing the fan angle also made the image better. And for example, here in this case, using different types of filters made slight changes. But for example, using different weighting schemes changed the image drastically, for example. So it was always better to use the Parker type in our image. And so this is, for example, the reconstruction, the filtered back projection that we applied to our chest image. Although again, it is not very successful, we can still see some features of the image successfully here. And we were also able to change a lot of features. So we can also consider this as a successful attempt of reconstruction. Now we can move on to our demo showing the working principles of these external codes and also the filtering types. And finally, we can talk about our project, our achievements and result interpretations as a part of discussion. So first of all, in this project, we were able to simulate non-idealities, real-life conditions, and the actual projection and filtered back projection procedures of a CT scanner, so that we were able to implement a successful CT, FEM-beam CT simulator. And we also used 3 data sets. And in these data sets, 2 of the images were actual body CT images, and 1 of them was a phantom image, which means that it was synthetic. But overall, a CT simulator was successfully implemented in MATLAB, and we were able to see its different non-idealities and different parameters. And also in class, we covered parallel beam CT, and we did not talk much about different parameters of CT or, for example, its non-idealities. So by doing this project, we were able to put on top of what we have covered in class, and we have discovered a different CT geometry. And as for the failures, as we have just seen in the demo part, the back projections created by the external codes were not very successful in their reconstructions, but at the same time, the features of the images were observable in these reconstructions, so that it can be considered as a successful attempt. And finally, as for the further improvements, first of all, we can, as for the noise part, we can try eliminating the noise much better. Or for example, different geometries can be added on top of this project in order to perform different geometries of CT, for example, cone beam. And also, for example, the external codes can be improved in order to correct its performance and use it more successfully as a part of our project, along with our handwritten projection codes. And these are our references. Thank you so much for listening to us and our project.